Understanding algorithm efficiency through asymptotic notations. In the world of computing, the speed and scalability of algorithms determine whether a program runs smoothly or grinds to a halt. At the heart of this evaluation lies algorithm analysis, which quantifies how efficient an algorithm is in terms of time and space requirements. This process involves studying the relationship between the input size of a problem and the computational resources needed to solve it. By focusing on growth rates rather than absolute numbers, we can compare algorithms across different scenarios and choose those optimized for specific tasks. The role of time complexity in algorithm design. Time complexity measures how long an algorithm takes to complete relative to the size of its input. It answers the critical question: how does execution time grow as the number of inputs increases? A commonly used metric for expressing time complexity is Big O notation. This standard allows developers to describe the upper bound of an algorithm's runtime, providing insight into its worst-case behavior. Example: consider sorting a list of integers. Bubble sort has a time complexity of $O n squared, meaning its performance deteriorates rapidly as the list grows. In contrast, quicksort typically operates at $O n\log n, making it significantly faster for larger datasets. One constant time, operations take the same amount of time regardless of input size, such as accessing an array element via index. Log and logarithmic time, algorithms like binary search have the problem space repeatedly, leading to extremely fast scaling. N linear time, simple loops iterate once over all input items, useful for sequential processing. N superscript 2 quadratic time, nested loops cause runtime to increase exponentially with growing input sizes. Important note: while Big O focuses on the worst-case scenario, other notations like $omega denote best-case behavior and $theta represents tight bounds where both upper and lower limits converge. Evaluating space complexity for resource management. If time complexity determines how quickly an algorithm executes, then space complexity reveals how much memory it consumes during operation. Efficient use of RAM is vital, especially when dealing with large-scale systems or constrained environments like mobile apps or embedded devices. An algorithm's space complexity considers both the input size and additional memory allocations made internally. For instance, recursive functions may require stack frames proportional to the depth of recursion, adding overhead beyond raw data storage. Comparing data structures based on memory usage. Different data structures exhibit varying levels of space efficiency. An unsorted array requires fixed size allocation, whereas dynamic arrays expand as elements are added, a feature managed by most modern languages automatically. Case study: hash tables offer near constant lookup times, $1, but their underlying implementation often reserves extra capacity to accommodate collisions gracefully. This results in higher initial memory consumption compared to simple arrays storing exactly n items. Similarly, graph representations vary widely, from adjacency matrices requiring $O n superscript 2 space to edge lists needing only $O e memory where e is the number of edges. Choosing wisely ensures your solution doesn't waste precious cache lines or trigger excessive page faults. Mastery of asymptotic notations for real-world applications. Proficiency in reading and applying asymptotic notations becomes indispensable when optimizing complex programs. These tools enable engineers to identify bottlenecks quickly without diving into line-by-line profiling sessions. For example, understanding that Dijkstra's shortest path algorithm operates at $O v plus e \log v helps prioritize improvements around priority queue operations rather than unnecessary pre-processing steps. When precision matters most. While Big O provides high-level guidance, there are situations where precise measurements become necessary. Parallel computing frameworks benefit immensely from knowing exact thread contention patterns or synchronization delays caused by lock acquisition frequencies. Moreover, cryptographic libraries rely heavily on accurate timing information to prevent side-channel attacks, an area where approximations might lead to exploitable vulnerabilities if misapplied. Breaking down common misconceptions about algorithm performance, many developers mistakenly equate faster execution times with better algorithms. However, context plays a pivotal role. What works well for small test cases may falter dramatically when applied to massive production workloads. Reality check and $O, n squared, $selection sort might outperform a theoretically superior $O, n \log n, $merge sort on tiny datasets due to smaller constant coefficients hiding behind the big O symbol. Recognizing these nuances prevents premature optimization traps where you spend hours tweaking minor inefficiencies while ignoring actual root causes impacting overall system performance. Tight bounds matter. Prefer algorithms with tighter theta bounds unless forced otherwise. A guaranteed $O, n, guarantee beats possible $O, n squared, outcomes even if average cases match. Constant factors can't be ignored forever. When comparing similarly rated methods, e.g., radix sort versus counting sort, account for multiplier differences affecting real-world speeds despite identical asymptotics. Hardware characteristics influence decisions. Cache locality advantages of certain loop orders, like row major order in matrix multiplication, shouldn't be overlooked simply because they're invisible to pure math-based analyses. Benchmarking techniques beyond theoretical limits to truly understand how an algorithm behaves, combining analytical approaches with empirical testing proves invaluable. Profiling tools like prof or built-in language-specific debuggers reveal hotspots missed entirely during abstract modeling phases. Best practices: always run benchmark suites across several representative sample sets containing typical edge cases found in live data. Relying purely on synthetic tests risks missing issues arising from non-uniform distributions seen frequently in practice. Interpreting benchmark results accurately, beware of misleading graphs showing erratic spikes attributed solely to random fluctuations unrelated to your algorithm itself. Use statistical techniques such as bootstrapping to extract meaningful trends from noisy measurement logs. Additionally, consider warm-up periods when measuring JIT-compiled code paths, since just-in-time optimizations introduce significant variance until full compilation completes after repeated invocations. The impact of algorithmic choices on system scalability. Scalable architectures depend critically upon sound algorithm design principles. Whether building distributed databases or microservices APIs, selecting components with predictable growth characteristics ensures smooth horizontal scaling capabilities. Suppose you're designing a recommendation engine handling millions of users daily. Opting for nearest neighbor calculations involving cosine similarity could soon become impractically slow unless replaced with approximate nearest neighbor algorithms offering acceptable error margins. Such decisions impact infrastructure budgets considerably. Replacing naive exponential time solutions with sublinear ones reduces server farm requirements substantially while maintaining service-level agreements regarding response latencies. Cross-disciplinary insights from related fields. Algorithm analysis draws inspiration from diverse disciplines including mathematics, physics, and economics. Studying Markov chains offers new perspectives toward probabilistic analysis models, while game theory contributes strategic thinking applicable in competitive algorithm settings. Even biological sciences provide interesting parallels. For instance, evolutionary computation leverages natural selection mechanisms mirroring genetic inheritance patterns observed among species adapting to environmental changes over generations. Learning from nature-inspired optimization strategies. Bee colony algorithms mimic swarm intelligence behaviors exhibited by honeybees searching collectively for food sources. Applying similar principles enables finding globally optimal configurations efficiently across vast parameter spaces. Ant colony optimization systems simulate pheromone trail-laying processes employed by ants navigating mazes to reach food supplies safely. These bio-inspired methods excel particularly well at solving combinatorial problems plagued traditionally by NP-hardness challenges. Educational resources and communities focused on advancing algorithm knowledge. Continuous learning remains central to staying ahead in this ever-evolving field. Engaging regularly with online communities fosters collective wisdom sharing among enthusiasts worldwide working collaboratively towards advancing algorithmic literacy. Platforms like Stack Overflow host vibrant discussions addressing nuanced questions spanning algorithmic design choices under various application contexts. Meanwhile, GitHub repositories showcase open-source implementations facilitating hands-on experimentation with proven methodologies. Pursuing advanced studies through formal education channels. Formal courses offered through prestigious institutions delve deeply into topics ranging from randomized algorithms to parallelism paradigms. Specialized tracks focusing exclusively on algorithmic complexity theory equip graduates thoroughly prepared tackling research-grade problems facing industry leaders today. Online platforms like Coursera and edX provide flexible alternatives allowing professionals to enhance skills conveniently from anywhere globe-wide without compromising quality standards. Expected academically rigorous curricula. Conclusion: mastering algorithm analysis empowers programmers to craft elegant yet highly performant software capable of meeting stringent demands imposed by modern technological landscapes. This journey begins with grasping fundamental concepts governing time and space complexities. By consistently practicing with real-world coding exercises while referring back to foundational theories whenever uncertainties arise, practitioners gradually build intuitive understanding enabling informed decision-making when faced with architectural dilemmas involving competing priorities.